Hello there, and welcome to the Soft Science Sanctuary. Tonight, we drift back through the mists of deep time to an era when our world wore a different face. An age when vast sheets of ice, miles thick, crept slowly across continents, transforming everything they touched. The Great Ice Age was not a single frozen moment, but a long conversation between Earth and climate, playing out across hundreds of thousands of years. During this time, glaciers advanced and retreated in grand cycles, each leaving its mark upon the land. Mountains were ground smooth, valleys were carved deep, and entire landscapes were reshaped by the patient, unstoppable power of moving ice. Tonight, we'll trace the journey of these ancient glaciers from their quiet beginnings as gentle snowfall to their transformation into rivers of ice that could crush mountains. We'll walk beside them as they inch across the world, listen to the silence of their slow advance, and witness the beauty they left behind when they finally melted away. If you enjoy these gentle journeys through time and science, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one curious soul at a time. But for now, let your breathing slow. Let the warmth of the present fade just a little, and allow yourself to drift backward into the deep cold of Earth's frozen past. Let's begin. The ice ages were not continuous cold, but cycles of freezing and thawing. When we speak of the Ice Age, we often imagine a single, unbroken span of cold, but the truth is more complex and more beautiful. Earth has experienced several ice ages throughout its long history, and within each, the climate pulsed in rhythmic cycles. Periods of intense cold when glaciers advanced, alternated with warmer intervals when the ice retreated. The most recent ice age, the one that shaped the world we recognize today, began about 2.6 million years ago, and technically continues even now, though we live in a warm, interglacial period. Within this span, glaciers have advanced and retreated dozens of times, each cycle lasting tens of thousands of years. These oscillations were driven by subtle shifts in Earth's orbit and tilt, changes so gradual they would be invisible in a human lifetime, yet powerful enough to tip the planet between ice and warmth. The ice did not descend all at once like a curtain, but crept forward season by season, year by year, century by century, in a dance choreographed by astronomy and atmosphere. A single snowflake can begin the birth of a glacier. Every glacier, no matter how vast, begins with something almost weightless: a snowflake. One frozen crystal settling softly onto the ground, then another and another. In places where more snow falls in winter than melts in summer, the layers begin to accumulate. Year after year, the snow piles deeper. The weight of new layers presses down on the old, squeezing out air and compacting the delicate crystals into denser, granular ice called firn. Over decades and centuries, the firn continues to compress, becoming harder, clearer, more solid. Eventually, it transforms into glacial ice, dense enough that it appears blue when light penetrates its depths. This process is slow beyond imagining. A glacier may take thousands of years to form, each layer a page in a frozen diary of climate. When scientists drill into ancient ice, they can read this record, layer by layer, tracing the history of Earth's atmosphere backward through time. From a single flake to a river of ice miles thick, the journey is one of patience and accumulation. A reminder that even the mightiest forces begin with the smallest, quietest acts. Glacial ice appears blue because it absorbs other colors of light. When you stand before a glacier, one of the first things you notice is its color. Not the white of fresh snow, but a deep, luminous blue that seems to glow from within. This blue is not paint or pigment, but a product of physics and time. As snow compresses into glacial ice over centuries, air bubbles are squeezed out, creating ice so dense that light behaves differently within it. When sunlight enters the glacier, the ice absorbs the longer wavelengths, the reds and yellows, allowing only the shorter blue wavelengths to pass through or reflect back. The deeper and older the ice, the more intense the blue becomes. In crevasses and ice caves where light filters through thick walls of ancient ice, the color can be so vivid it feels almost unreal, as though the glacier holds trapped pieces of the sky. This blue is the signature of time itself, a visual echo of thousands of years of compression and crystallization. It is one of the quietest, most beautiful reminders that ice is not simply frozen water, but a living archive of Earth's frozen past. Glaciers move, though their motion is invisible to the eye. Standing before a glacier, it appears utterly still, a frozen monument locked in place. But beneath that motionless surface, something extraordinary is happening. The glacier is moving, flowing like a river, though so slowly that no human eye could detect it in a single glance. The movement occurs because ice, under immense pressure, behaves almost like a very stiff fluid. The weight of accumulated snow and ice presses down on the layers below, causing them to deform and flow outward or downhill. Near the surface, the ice remains brittle and can crack, forming deep crevasses. But deeper down, it flows in slow, plastic motion. Some glaciers move only a few centimeters per day. Others, where slopes are steep or ice is thick, can travel several meters in the same span. Over years, this adds up. A boulder trapped in the ice might journey miles from where it first fell, carried along in the glacier's patient grip. This movement is what gives glaciers their power to reshape the land. As they flow, they scrape and grind, carving valleys and polishing bedrock, leaving behind a signature that endures long after the ice has melted away. The weight of glacial ice is almost incomprehensible. Imagine a sheet of ice 2 miles thick stretching across an entire continent. The weight pressing down on the land beneath is so immense it actually deforms the Earth's crust, pushing it downward into the mantle below. This is not metaphor, it is geology. During the peak of the last glacial maximum, about 20,000 years ago, massive ice sheets covered much of North America, Europe, and Asia. In some places, the ice was more than 3 kilometers thick. The sheer mass was enough to depress the land by hundreds of meters, creating deep basins that would later fill with water as the ice retreated. Even now, long after the ice has melted, the land is still slowly rising in a process called isostatic rebound. Scandinavia, for example, continues to rise by several millimeters each year, gradually recovering from the weight it bore during the Ice Age. This rebound will continue for thousands of years more. The weight of ice is a reminder that glaciers are not just surface features. They are forces powerful enough to bend the very bones of the planet. Glaciers carve U-shaped valleys as they move. Rivers carve valleys too, but the valleys they create are V-shaped, narrow at the bottom and widening toward the top. Glaciers, by contrast, sculpt something entirely different. As a glacier moves through a mountain valley, it grinds away rock not just at the bottom, but along the sides as well, widening and deepening the passage. The result is a U-shaped valley with steep, nearly vertical walls and a broad, flat floor. These valleys are among the most recognizable signatures of glacial activity, visible across landscapes that were once covered by ice. Yosemite Valley in California is a perfect example. Its sheer granite cliffs and wide, open floor were carved by glaciers that flowed through the region during the Ice Age. When the ice finally melted, it left behind a landscape of breathtaking scale and beauty. Glacial valleys are often deeper than the surrounding land, and when the ice retreats, they may fill with water, creating long, narrow lakes. These valleys stand as monuments to the slow, grinding power of ice, reminders that patience and persistence can reshape even the hardest stone. Fjords are glacial valleys that have been flooded by the sea. In places where glaciers carved valleys all the way to the ocean, something remarkable happens when the ice retreats. The sea rushes in to fill the deep trench left behind, creating a fjord, a narrow inlet with steep cliffs rising on either side. Fjords are some of the most dramatic landscapes on Earth. Norway's coast is lined with them, each one a deep, narrow channel cutting far inland, their walls plunging hundreds of meters into dark water. The cliffs are often so steep that waterfalls tumble directly from the heights into the sea below. These formations were carved over tens of thousands of years as glaciers ground their way through solid rock, deepening valleys far below sea level. When the ice melted, the ocean claimed what the glacier had hollowed out, transforming valleys into sheltered waterways. Fjords are not just beautiful. They are geological time made visible, each one a record of ice, stone, and the slow, inevitable reshaping of the world. Glaciers carry rocks and boulders vast distances. As a glacier flows, it does not move alone. It carries with it everything it encounters: boulders, gravel, sand, and silt, all locked within the ice or pushed along at its base. Some of these rocks may travel hundreds of miles from their place of origin, carried slowly but inexorably by the glacier's motion. When the ice finally melts, it deposits this material in scattered piles and ridges. Geologists call these deposits moraines, and they can stretch for miles, marking the former extent of glaciers long vanished. Some boulders, called glacial erratics, are left sitting alone in landscapes where no similar rock exists, travelers from distant mountains delivered by ice. These erratics puzzled scientists for centuries. How could a massive boulder appear in the middle of a flat plain, far from any source of such stone? The answer, once understood, was one of the key insights that helped unlock the story of the Ice Ages. Today, glacial erratics stand as silent witnesses to journeys that took thousands of years, monuments to the slow and steady power of moving ice. The Ice Age lowered global sea levels by hundreds of feet. When glaciers grow, they do not simply sit on the land. They pull water from the ocean, locking it away in frozen form. During the peak of the last Ice Age, so much water was trapped in glaciers that global sea levels dropped by more than 120 meters, nearly 400 feet. This dramatic fall exposed vast areas of continental shelf that are now submerged. Land bridges appeared between continents. Alaska and Siberia were connected by a wide plain called Beringia, allowing plants, animals, and eventually humans to migrate between Asia and North America. Britain was not an island, but part of the European mainland. Rivers extended their courses far out onto the exposed shelf, carving valleys that are now underwater canyons. Coastlines were miles or even hundreds of miles farther out than they are today. When the ice finally melted, the seas rose again, flooding these low-lying lands and redrawing the map of the world. The coastlines we know today are a product of that melting, a temporary configuration in the long rhythm of ice and water. Glaciers create landforms called drumlins as they flow over sediment. Beneath a moving glacier, immense pressure and friction shape the landscape in subtle ways. When a glacier flows over loose sediment, it can mold the material into smooth, elongated hills called drumlins. These hills are shaped like inverted spoons, with a steep end facing the direction from which the ice came, and a tapered tail pointing in the direction of flow. Drumlins often appear in groups, forming what geologists call drumlin fields, clusters of these streamlined hills, all aligned in the same direction. Their shape reveals the path of ancient glaciers, frozen arrows pointing the way the ice once moved. From the air, drumlin fields create striking patterns, a landscape sculpted by forces no longer present. Ireland, Canada, and the northern United States are dotted with these formations, each one a quiet testament to the grinding passage of ice. Though small compared to mountains, drumlins are powerful reminders that glaciers do not simply carve and crush. They also build, shaping the land with an artist's precision. Ice cores reveal ancient climate history trapped in layers. Deep within the ice sheets of Greenland and Antarctica, scientists drill long cylinders of ice called ice cores. These cores can reach depths of several kilometers, and each layer within them represents a single year of snowfall, compressed and preserved. By analyzing the chemistry of the ice, tiny bubbles of ancient air, and trace elements within each layer, researchers can reconstruct the climate of the past with astonishing precision. They can measure temperature, atmospheric composition, and even volcanic eruptions that occurred tens of thousands or even hundreds of thousands of years ago. One of the most famous ice cores, drilled at a site in Antarctica called Vostok, extends back more than 400,000 years, revealing 4 complete glacial cycles. The patterns are clear. Earth's climate has oscillated between cold and warm in a rhythm driven by orbital changes and amplified by feedback loops in the atmosphere and oceans. These cores are windows into deep time, allowing us to see not just what happened, but how and why. They are among the most valuable records of Earth's history. Each layer a page in the frozen diary of our planet. The Milankovitch cycles explain the timing of ice ages. For much of history, the cause of ice ages remained a mystery. Why did the ice advance and retreat in cycles? What triggered these great shifts in climate? The answer came from a Serbian mathematician named Milutin Milankovitch, who spent decades calculating how changes in Earth's orbit and axial tilt affect the distribution of sunlight across the planet. He identified 3 key cycles. The shape of Earth's orbit around the Sun changes over about 100,000 years. The tilt of Earth's axis oscillates over about 41,000 years. And the wobble of Earth's axis, like a spinning top, cycles every 26,000 years. Individually, these changes are small, but together they influence how much sunlight reaches different parts of the planet, especially the high latitudes where ice sheets grow. When conditions align to reduce summer sunlight in the north, snow persists through the warm season, accumulating year after year until glaciers begin to form. Milankovitch's work was initially dismissed, but decades later, ice core data confirmed his predictions with stunning accuracy. The cycles he described matched the timing of glacial and interglacial periods almost perfectly. These orbital rhythms are the metronome of ice ages, the quiet celestial clockwork that tips Earth between warmth and cold. Glaciers grind rock into fine powder called glacial flour. As a glacier moves, it scrapes across bedrock with immense force, pulverizing stone into a fine, silty powder. This powder is so fine that it can remain suspended in water for a long time, giving glacial rivers and lakes a distinctive milky, turquoise color. This substance is called glacial flour or rock flour, and it is one of the byproducts of the glacier's slow, grinding motion. The particles are smaller than sand, almost like talc, and they carry minerals ground from the bedrock over which the glacier traveled. When glacial meltwater flows into lakes or oceans, the flour spreads through the water, scattering light and creating the vivid colors often seen in glacial lakes. Lake Louise in Canada, for example, owes its famous turquoise hue to glacial flour suspended in its waters. The flour eventually settles to the bottom, forming thick layers of sediment that can be studied to understand the history of glacial movement. Even after the ice is gone, the flour remains, a fine dust that tells the story of stone meeting ice and ice winning, grain by grain. The ice sheets of the last glacial maximum covered millions of square miles. At the height of the last ice age, roughly 20,000 years ago, ice sheets blanketed vast regions of the northern hemisphere. The Laurentide ice sheet covered most of Canada and extended south into the northern United States. The Fennoscandian ice sheet buried Scandinavia, Britain, and parts of northern Europe. Smaller ice caps covered mountain ranges across the world. Together, these ice sheets contained about 3 times as much ice as exists on Earth today. They were so massive that they reflected sunlight back into space, cooling the planet further and reinforcing their own growth. The landscape beneath the ice was entirely transformed. Forests were buried, rivers were dammed or rerouted. Entire ecosystems were pushed southward or extinguished. The weight of the ice depressed the land, creating basins that would later become the Great Lakes and the Baltic Sea. To stand at the edge of such an ice sheet would have been to face a wall of ice, stretching to the horizon in every direction, a frozen continent resting atop the land, silent and seemingly eternal. Glacial ice can be hundreds of thousands of years old. Near the surface of a glacier, the ice is relatively young, perhaps only decades or centuries old. But deep within the ice sheet, beneath layers of accumulated snow and compression, the ice is ancient. Some of the ice at the base of the Antarctic ice sheet is estimated to be nearly 1 million years old. This ice has been locked away from the atmosphere for longer than modern humans have existed. The air bubbles within it contain samples of the ancient atmosphere, snapshots of what the air was like when that snow first fell. By studying these bubbles, scientists can measure past concentrations of carbon dioxide, methane, and other gases, tracing the evolution of Earth's climate across deep time. The age of the ice increases with depth, but only to a point. Eventually, the pressure and heat at the base of the ice sheet becomes so great that the ice begins to melt, erasing the oldest layers. Still, what remains is an extraordinary archive, a library of climate written in frozen water. To touch glacial ice is to touch the past, a substance that has endured, unchanged, through centuries or millennia, waiting to tell its story. Glaciers create kettle lakes when ice blocks are buried and later melt. As glaciers retreat, they do not always melt evenly. Sometimes large blocks of ice become detached from the main glacier and are buried beneath sediment and debris. These buried ice blocks can remain frozen for decades or even centuries, insulated by the material around them. Eventually, the ice melts and the ground above it collapses, creating a depression. If the depression is deep enough and the water table is high, it fills with water, forming what is called a kettle lake. Kettle lakes are often small, circular, and deep, with steep sides and clear water. They dot landscapes across the northern United States, Canada, and Europe, remnants of the last glacial retreat. Some are filled with water year-round, while others may dry up seasonally. These lakes are ecological treasures, often hosting unique plant and animal communities. They are also geological reminders of the Ice Age, quiet pools marking the spots where ancient ice once rested, hidden beneath the earth. The weight of ice can trigger earthquakes as it melts. As glaciers grow, they press down on the Earth's crust with immense weight. But when they melt and that weight is lifted, the crust begins to rise again in a process called isostatic rebound. This rising is not always smooth. The The release of pressure can trigger earthquakes as the crust adjusts to its new configuration. In regions where ice sheets have recently melted, such as Scandinavia and parts of North America, scientists have documented increased seismic activity. These earthquakes are generally not large, but they are a direct consequence of the ice's retreat. Even today, thousands of years after the ice began to melt, the land is still adjusting. Greenland, where the ice sheet is currently losing mass, has seen a rise in earthquakes as the bedrock rebounds. The connection between ice and earthquakes is a reminder that glaciers are not isolated features. They are part of a dynamic system that includes the solid Earth itself, and their presence or absence can reshape not just the surface, but the very structure of the land. Glaciers once covered regions that are now deserts. It may seem impossible, but glaciers once existed in places that are now among the driest on Earth. During past ice ages, the distribution of ice was not limited to the poles. Mountain ranges in regions that are now arid, such as the Sahara and parts of the Middle East, hosted glaciers. The climate during glacial periods was not uniformly cold. Instead, atmospheric circulation patterns shifted, bringing different weather to different regions. Some areas became wetter, allowing glaciers to form even at relatively low latitudes, especially in mountainous terrain. Evidence of these ancient glaciers remains in the form of moraines, erratic boulders, and U-shaped valleys carved into rock. These features stand in stark contrast to the barren, sun-scorched landscapes that surround them today. They are reminders that Earth's climate is not static, but constantly shifting. What is desert today was once ice. What is ice today may one day bloom with life. The planet's face changes slowly but completely across the long arc of time. Glacial meltwater carves deep channels called meltwater channels. As glaciers melt, the water has to go somewhere. During the Ice Age, massive volumes of meltwater surged across the landscape, carving deep channels and valleys. These meltwater channels can be enormous, cutting through solid rock and reshaping entire regions in a matter of days or weeks. One of the most dramatic examples is the channeled scablands in Washington state. At the end of the last ice age, a glacial lake called Lake Missoula, dammed by ice, suddenly burst through its barrier. The resulting flood released a volume of water equivalent to all the rivers in the world combined, moving at speeds up to 60 miles per hour. The floodwaters scoured the landscape, tearing away soil, carving deep gorges, and depositing boulders the size of houses. The scars left by this flood are still visible today, a testament to the catastrophic power of glacial meltwater. Similar floods occurred in other regions as ice dams failed and glacial lakes emptied. These events reshaped continents, creating landforms that continue to puzzle and amaze geologists. Glaciers can preserve ancient organisms in ice for millennia. Within the ice, life can be frozen in time. Glaciers have preserved the bodies of animals, plants, and even microorganisms for thousands or tens of thousands of years, encasing them in cold, airless conditions that prevent decay. Mammoths with their fur and flesh intact have been found frozen in Siberian ice. Ancient mosses and insects perfectly preserved emerge as glaciers retreat. In some cases, DNA can still be extracted from these specimens, offering glimpses into the biology of species long extinct. These frozen archives are invaluable to science. They allow researchers to study organisms as they were in life, not just as fossils. They provide insights into ancient ecosystems, climates, and evolutionary histories. But as glaciers continue to melt in the warming climate, these preserved remains are being exposed and lost to decay. The ice that protected them for so long is now releasing them back into the world, where time quickly reclaims what it once paused. Each discovery is a race against time, a chance to learn from the frozen past before it vanishes forever. The term Ice Age can refer to both long periods and short cycles. The language of ice ages can be confusing. Strictly speaking, an ice age is a long period during which Earth has permanent ice sheets at its poles. By this definition, we are still in an ice age today, one that began about 2.6 million years ago. Within this ice age, however, are shorter cycles of colder and warmer periods. The cold phases when glaciers advance are called glacials, or glacial periods. The warm phases, like the one we live in now, are called interglacials. The last glacial period, often called the last glacial maximum, peaked about 20,000 years ago. The current interglacial, called the Holocene, began about 11,100 years ago and has been marked by relatively stable, warm temperatures that allowed human civilization to flourish. Understanding this terminology helps clarify the story of ice and climate. We are not in a cold phase of an ice age, but in a warm pause within a much longer frozen era. Glacial periods covered about 90% of the last million years. For most of the past million years, Earth has been colder than it is today. Glacial periods, when ice sheets expanded across continents, have dominated the climate record. The warm interglacials, like the one we currently enjoy, are brief interludes, typically lasting only 10,000 to 20,000 years. This means that the climate we consider normal, the stable, temperate conditions that have allowed agriculture and cities to thrive, is actually the exception rather than the rule. For most of recent Earth history, vast ice sheets have been the norm. The regularity of these cycles, driven by the Milankovitch orbital rhythms, suggests that without human influence, Earth would eventually slide back into another glacial period. However, the current rise in atmospheric carbon dioxide from human activity is disrupting this natural cycle, potentially delaying or even preventing the next glaciation. The story of ice is not over. It is simply paused, waiting for the next turn of the celestial gears that govern climate. Glaciers can advance even during overall warming trends. Not all glaciers behave the same way. While the global trend may be toward warming and glacial retreat, individual glaciers can still advance, depending on local conditions. An increase in snowfall in a particular region, for example, can cause a glacier to grow even if temperatures are rising elsewhere. This complexity is one reason why glaciers are such valuable indicators of climate. Each one responds to a unique combination of temperature, precipitation, and local geography. By studying many glaciers across different regions, scientists can piece together a more complete picture of climate change. Some glaciers are also fed by large ice fields or are influenced by ocean currents, factors that can cause them to behave differently from their neighbors. The Perito Moreno Glacier in Argentina, for instance, has remained relatively stable while others in the region have retreated. Glaciers remind us that climate is not uniform, but a mosaic of interconnected systems, each responding to forces both global and local. The albedo effect helps glaciers grow once they form. Ice is highly reflective. When sunlight strikes a glacier, much of that light bounces back into space rather than being absorbed. This reflectivity, called albedo, has a powerful effect on climate. The more ice there is, the more sunlight is reflected, and the cooler the planet becomes. This creates a feedback loop. Once ice begins to form, it reflects more sunlight, which cools the planet further, which allows more ice to form. This is one reason why glacial periods can intensify so dramatically once they begin. The opposite is also true. When ice melts, the darker land or ocean beneath is exposed, absorbing more sunlight and warming the surface. This accelerates further melting, creating a feedback loop in the opposite direction. Albedo effects are among the most important amplifiers of climate change, both during glaciation and deglaciation. They help explain why ice ages once begun can deepen quickly, and why the end of an ice age can be rapid and dramatic. Glaciers shaped the Great Lakes of North America. The 5 Great Lakes, Superior, Michigan, Huron, Erie, and Ontario, are among the largest freshwater lakes in the world. They were carved and shaped by the immense glaciers that covered North America during the last ice age. As the Laurentide ice sheet advanced, it scoured deep basins into the bedrock, following and deepening river valleys that already existed. When the ice finally retreated, these basins filled with meltwater, creating the vast lakes we see today. The Great Lakes hold about 20% of the world's fresh surface water, a legacy of glacial erosion and melting. Their shores, dotted with moraines and glacial till, bear the marks of the ice that shaped them. These lakes are not just geological features, they are ecosystems, economic resources, and cultural landmarks. They exist because ice, over tens of thousands of years, ground away solid rock and left behind voids that water eagerly filled. Glacial striations show the direction of ice flow. As glaciers move, rocks embedded in their base scrape across the bedrock below, leaving long, parallel scratches called striations. These marks can be remarkably straight and uniform, etched into stone with the precision of a chisel. Striations are one of the clearest signs of past glacial activity. They reveal not only that ice was once present, but also the direction it flowed. By mapping striations across a region, geologists can reconstruct the paths of ancient glaciers, tracing their advance and retreat across the landscape. These scratches can survive for thousands or even millions of years, preserved in hard rock long after the ice has vanished. Walking across striated bedrock is like reading the handwriting of glaciers, messages left by ice for those who know how to interpret them. Glaciers move faster in their center than at their edges. The flow of a glacier is not uniform. Ice in the center of the glacier, away from the friction of the valley walls, moves faster than ice at the edges. This creates a pattern of differential movement, with the center pulling ahead while the edges lag behind. This difference in speed can create stress within the ice, leading to the formation of crevasses, deep cracks that open where the ice is moving at different rates. Crevasses are most common near the surface, where the ice is brittle, while deeper ice flows more smoothly. The faster flow in the center is one reason why glaciers can transport material so effectively. Rocks and debris, caught in the central flow, are carried along more quickly than those near the edges, where the ice moves sluggishly or not at all. This internal motion is invisible from the surface, but it shapes the glacier's behavior and its ability to carve and reshape the landscape. The term glacial pace reflects the slow but unstoppable nature of ice. We use the phrase glacial pace to describe something that moves very slowly. The metaphor is apt. Glaciers advance at speeds that are imperceptible in the moment, yet unstoppable over time. A glacier might move only a few centimeters a day, a distance so small it vanishes in the scale of human perception. Yet over years, decades, and centuries, that motion accumulates. Valleys are carved, mountains are worn smooth, entire landscapes are rewritten. The patience of glaciers is humbling. They do not rush, they do not falter, they simply move, grinding forward with the weight of accumulated time, indifferent to obstacles, reshaping the world inch by inch. In this way, they teach a lesson about persistence. Even the smallest, slowest motion sustained long enough can move mountains. Glaciers create hanging valleys when tributaries cannot keep pace with the main glacier. In mountainous regions, smaller glaciers often feed into larger ones, like tributaries joining a river. But the larger glacier, with its greater volume and weight, carves its valley deeper and faster than the smaller tributaries can manage. When the ice melts, the tributary valleys are left hanging high above the main valley floor, their mouths perched on steep cliffs. Streams that once fed the glacier now tumble over these cliffs as waterfalls, plunging into the valley below. These hanging valleys are common in glaciated mountain ranges such as the Alps and the Sierra Nevada. They create some of the most dramatic and beautiful waterfalls in the world, cascades that fall hundreds or even thousands of feet in a single drop. Each hanging valley is a marker of the uneven power of glaciers, evidence that even ice flows at different speeds depending on volume and terrain. The retreat of glaciers can trigger massive floods. When glaciers melt, the water does not always flow away gently. Sometimes vast amounts of meltwater accumulate behind ice dams or within the glacier itself, forming temporary lakes. When these dams fail, the water is released in catastrophic floods called glacial outburst floods, or Jökulhlaups. These floods can be among the most powerful natural events on Earth. They carry enormous volumes of water along with boulders, sediment, and ice, sweeping away everything in their path. The speed and force of these floods can reshape entire valleys in hours or days. Iceland, with its many glaciers perched atop active volcanoes, experiences Jökulhlaups regularly. When volcanic heat melts the ice from below, the meltwater builds up until it bursts through the glacier's edge, racing toward the sea. These floods are reminders that glaciers are not static. They are dynamic, and their melting can be as dramatic and transformative as their advance. Glaciers once extended into the subtropics during ancient ice ages. The ice ages of the recent past are not the only ones Earth has experienced. Hundreds of millions of years ago, the planet endured even more severe glaciations, some so intense that ice may have reached nearly to the equator. During an event called Snowball Earth, which occurred roughly 700 million years ago, much of the planet's surface may have been covered in ice. Glacial deposits from this time have been found in regions that were near the equator during that era, suggesting that ice extended far beyond the poles. These ancient ice ages were driven by different mechanisms than the recent ones. Changes in atmospheric composition, the arrangement of continents, and the sun's luminosity all played roles. But the evidence is clear. Ice has shaped Earth's surface not just in recent millennia, but across vast stretches of geological time. The story of glaciers is not just the story of the last few million years. It is woven through the entire history of the planet. Some glaciers contain layered ice that reveals seasonal cycles. When snow falls on a glacier, it leaves a mark. Winter snow tends to be fine and densely packed, while summer snow may contain more dust or organic material. Over time, these differences create visible layers within the ice, like rings in a tree. By examining these layers, scientists can count backward through time, identifying individual years and even seasons. Each band of ice is a snapshot of the climate when that snow fell, preserving information about temperature, precipitation, and atmospheric conditions. This layering is most visible in ice cores, where the stratigraphy can be studied in detail. But even on the surface, where crevasses or melting expose the ice's interior, these bands can sometimes be seen, a visual record of time passing, layer by layer. Glacial erratics can be enormous boulders weighing thousands of tons. Among the most striking legacies of glaciers are the massive boulders they leave behind. These glacial erratics, some as large as houses, sit in landscapes where no similar rock exists, transported by ice from distant mountains. The size of some erratics is astonishing. Boulders weighing thousands of tons were carried by glaciers for miles, even hundreds of miles, and deposited when the ice melted. They rest on the surface, incongruous and unmistakable, like pieces of a puzzle from another place. For early geologists, erratics were one of the key clues that unlocked the Ice Age theory. No flood or landslide could have moved such massive objects across flat terrain. Only ice, moving slowly and with immense power, could have carried them. Today, these boulders are landmarks, often given names and treated with reverence. They are travelers from deep time, silent witnesses to journeys that took millennia. Glaciers can create ecosystems through the nutrients they release. As glaciers grind rock into fine sediment, they release minerals that were locked within the stone. When this sediment is carried by meltwater into rivers, lakes, and oceans, it provides nutrients that fuel the growth of plankton, plants, and entire food webs. In coastal regions where glacial rivers flow into the sea, the influx of nutrients can create highly productive ecosystems. Salmon, for example, thrive in rivers fed by glacial meltwater, which is cold, clear, and rich in minerals. Even on land, glacial till, the mixture of rock, clay, and sediment left behind by retreating glaciers, can be remarkably fertile. The grinding action of the ice creates a diverse mix of particle sizes and minerals, ideal for supporting plant growth. In this way, glaciers are not just destroyers, they are also creators, enriching the land and water with the gifts of groundstone, turning barren rock into the foundation for life. The retreat of glaciers exposes new land for colonization. When a glacier retreats, it leaves behind a raw, barren landscape. Rock, gravel, and silt, untouched by plants or soil organisms. But this emptiness does not last. Almost immediately, life begins to move in. First come the pioneer species, hardy plants like mosses and lichens that can survive on bare rock. They begin the slow process of breaking down stone into soil, adding organic matter as they live and die. Seeds carried by wind or birds take root, and gradually, more complex plants establish themselves. Animals follow. Insects, birds, and mammals move into the new terrain, creating food webs and shaping the emerging ecosystem. Over decades and centuries, what was once barren, ice-scoured rock becomes meadow, then forest, then a fully functioning ecosystem. This process, called ecological succession, is a testament to life's resilience and adaptability. Even the harshest, most desolate landscapes left by retreating glaciers eventually bloom with life. Glaciers can shape valleys even without moving forward. Even when a glacier is in retreat, it continues to shape the landscape. As the ice melts, it releases the rock and sediment it has been carrying, depositing it in ridges and mounds. Meltwater carves channels and reshapes the terrain, sorting sediment by size and depositing it in layers. The mere presence of ice, even stationary ice, influences the land beneath it. The weight compresses the soil, the cold preserves certain features, and the meltwater creates new ones. In this way, glaciers are constantly at work, sculpting and reshaping, whether they are advancing, retreating, or simply sitting still. Their influence is not limited to their motion. It extends to every aspect of their interaction with the land, water, and air around them. The Hubbard Glacier in Alaska is still advancing, while most glaciers around the world are retreating in response to warming temperatures. A few are still growing. The Hubbard Glacier in Alaska is one of them. Fed by a massive ice field and sheltered by local geography, it has been slowly advancing for decades. In 2002, the glacier advanced so far that it sealed off a fjord, creating a temporary lake. The advance was eventually reversed, but the event demonstrated that glaciers can still behave unpredictably, even in a warming world. The Hubbard Glacier is a reminder that glaciers are complex systems, influenced by factors beyond just temperature. Snowfall, terrain, and ice dynamics all play roles, and not every glacier responds to climate change in the same way. It stands as a living example of glacial power still carving and shaping the land as it has for thousands of years. Glaciers can create natural dams that hold back enormous lakes. When a glacier blocks a valley or river, it can create a natural dam, trapping water behind it and forming a glacial lake. These lakes can be enormous, holding millions or even billions of cubic meters of water. As long as the ice dam remains stable, the lake sits quietly behind it, growing deeper with each season's melt. But ice dams are inherently unstable. When they fail, the results can be catastrophic. The sudden release of a glacial lake can send a wall of water and debris racing down the valley, obliterating everything in its path. These outburst floods have destroyed towns, reshaped valleys, and left scars on the landscape that last for centuries. Glacial lakes are both beautiful and dangerous, serene pools held in place by the fragile architecture of ice. The ice at the base of a glacier can melt from geothermal heat. Even in the coldest climates, the base of a glacier can experience melting. The Earth's interior is hot, and that heat radiates upward through the crust. In places where ice is thick enough, the pressure and geothermal heat can cause the ice at the very bottom to melt, even though the surface remains frozen. This meltwater acts as a lubricant, allowing the glacier to slide more easily over the bedrock. It can also create channels and cavities beneath the ice, forming a hidden network of water that flows unseen. In some cases, this basal melting can trigger rapid glacier movement, as the ice loses its grip on the bedrock and begins to slide more freely. This is one of the factors that can cause glaciers to surge, advancing suddenly and dramatically before slowing again. The base of a glacier is a hidden world where ice, water, and rock interact in ways that shape the glacier's behavior from below. Glaciers can make musical sounds as they move and crack. Glaciers are not silent. They groan, crack, rumble, and sing. As the ice shifts and moves, it creates sounds that range from deep, resonant booms to high-pitched creaks and pops. These sounds are caused by the ice flexing, cracking, and scraping against rock. Crevasses open with sharp cracks. Ice blocks carve from the glacier's edge with thunderous roars. Meltwater streams gurgle and rush through channels within the ice. Together, these sounds create a symphony of motion, a constant reminder that glaciers are alive with activity. For those who spend time near glaciers, these sounds become familiar, even comforting. They are the voice of ice, speaking in a language of pressure, motion, and transformation. Glacial landscapes attract unique forms of life. The harsh, cold environments created by glaciers are home to specialized organisms that thrive where few others can. Ice worms, for example, live within the ice itself, feeding on algae and bacteria. They cannot survive in warm temperatures. Their bodies adapted entirely to life in the cold. Algae can also grow on glacial ice, forming colorful blooms of red, green, or pink that tint the snow and ice. These algae are specially adapted to withstand freezing temperatures and intense UV radiation. Birds, mammals, and insects also live near glaciers, taking advantage of the meltwater and the unique conditions created by the ice. Ptarmigans, marmots, and even bears can be found in glacial regions, each adapted to the challenges of life in the cold. Glacial environments are not barren wastelands. They are ecosystems, hosting forms of life that have found ways to thrive in one of the planet's harshest environments. The Little Ice Age was a period of glacier advance in recent centuries. Between roughly 1300 and 1850, Earth experienced a period of cooler temperatures known as the Little Ice Age. During this time, glaciers around the world advanced, expanding into valleys and covering land that had been ice-free for centuries. the Little Ice Age was not a true ice age in the sense of continental ice sheets, but it was a significant climatic event. Winters were colder, growing seasons shorter, and glaciers in the Alps, Scandinavia, and other regions grew larger. The causes of the Little Ice Age are still debated, but may include reduced solar activity, increased volcanic eruptions that blocked sunlight, and natural variability in ocean circulation. As temperatures warmed again in the 19th and 20th centuries, the glaciers retreated, leaving behind moraines and other evidence of their temporary expansion. The Little Ice Age is a reminder that climate is always changing, even on human timescales. Modern glaciers are retreating faster than at any time in recorded history. Today, the vast majority of glaciers around the world are shrinking. Warmer temperatures driven by human activity and the increase of greenhouse gases in the atmosphere are causing glaciers to melt at unprecedented rates. Glaciers that took thousands of years to form are disappearing in decades. Ice that once filled valleys and covered peaks is now reduced to fragments. Meltwater streams that once flowed year-round are drying up. The retreat of glaciers has consequences beyond the ice itself. It affects water supplies for millions of people, contributes to rising sea levels, and alters ecosystems that depend on glacial meltwater. Watching glaciers retreat is like watching time accelerate, a reminder that the slow forces that shaped the Ice Age are being overwhelmed by the rapid changes of the present. Glaciers are among the most sensitive indicators of climate change. Because glaciers respond directly to temperature and precipitation, they are among the most reliable indicators of climate conditions. When glaciers grow, it signals a cooler, snowier climate. When they retreat, it indicates warming. Scientists monitor glaciers around the world, measuring their length, thickness, and mass balance to track changes over time. These measurements provide valuable data about how the climate is changing and how quickly. Glaciers also preserve a record of past climate within their ice, offering a window into conditions long before human records began. Together, these sources of information make glaciers one of the most important tools for understanding both past and present climate. They are the planet's memory, written in ice, slowly melting into the present. And so we arrive at the end of our long journey through the ice. We have walked beside glaciers as they formed from the first snowflake, grown heavy with time, and crept across continents. We have seen them carve valleys, grind mountains, and reshape the face of the earth. We have watched them retreat, leaving behind lakes, rivers, and landscapes of breathtaking beauty. The Ice Age was not a single event, but a rhythm, a slow pulse of cold and warmth that has played across Earth for millions of years. And though we live in a warm interlude, the ice has not truly left us. It lingers in the poles, in high mountains, in the deep cores that hold the memory of the past. The story of glaciers is the story of patience and power, of transformation measured not in moments, but in millennia. It is a reminder that even the hardest stone yields to the slow, steady pressure of time, and that the world we see around us is not permanent, but forever in motion. As you drift towards sleep tonight, let the quiet rhythm of the glaciers carry you. Imagine the slow creak of ice, the whisper of snow, the deep silence of a world blanketed in white. Let your thoughts grow still, like a frozen lake beneath the stars. If you found peace in this journey through time, consider liking, subscribing, or sharing a thought below. It helps others find their way to this quiet corner of science, one sleepy soul at a time. But for now, there is nothing more to do. The ice has told its story. The world continues to turn slowly, patiently, carrying all of us forward through time. Rest well and dream of deep time, of glaciers, of the quiet beauty of a planet forever reshaping itself. Good night.